Last time, when we were discussing series, we saw that it was hard to find its sum, the actual numerical value the infinitely many terms of the series add up to. We were able to do it for a few special series, telescoping series and geometric series, but that's about it. And for the most part, we can't do it. Although determining the sum of a series is difficult, it turns out it is not so hard to merely decide whether a series converges or not, i.e. whether its sum is finite or is infinite or worse. We encountered one simple test to do just that already, the test for divergence, which says a series diverges if its individual terms as a sequence do not converge to zero. But, if you recall, the test for divergence was precisely that, a test for divergence, meaning it is incapable of determining that a series converges. Either it's sure that a series diverges, or it's inconclusive. But now we'll turn to a more robust test that is actually able to decide convergence and divergence. It's called the integral test. So what does the integral test say? Roughly, it states that if you convert an infinite series into an analogous integral, the series converges if the integral converges, and the series diverges if the integral diverges. More precisely, it says that given a series whose terms, a sub n, are determined by a function f that is continuous, positive, and decreasing on the interval from 1 to infinity, then the series and the improper integral of f from 1 to infinity either both converge or both diverge. That is, the series and the integral share the same convergence status. The upshot of this test is that although determining the sum of a series is hard, evaluating an integral is, relatively speaking, easy. However, it's important to note that this does not mean that the sum of a series equals the value of the improper integral. It just says that the convergence, or divergence, of each is linked. But why does the integral test work at all? Admittedly, the test seems fairly intuitive, and it states more or less what we might have guessed if we managed to think of it. But still, intuition is not proof, and ultimately, an improper integral is a different beast than an infinite series. So why do they agree with each other regarding convergence? Let's take a concrete example. Suppose we want to decide whether the harmonic series converges, that is, the series 1 plus a half plus a third, and so on. According to the integral test, we would consider the function 1 over x and integrate it from 1 to infinity. That corresponds to the area of this blue region. Let's say we want to approximate this area using left-oriented Riemann rectangles of width 1. Since these rectangles all have a width 1, their areas are the same as their heights, and their heights are given by the height of the curve 1 over x at the rectangle's leftmost edge. This means our first rectangle has area 1, the next has area 1/2, and then 1/3, and so on. Thus, the total area of the rectangles is the same as the sum of the harmonic series. Now, remember that we already know the true area under the 1 over x curve is infinite, since the integral gives us a natural log which goes to infinity. But if we look at our rectangles, they stick up over the blue region, thus overestimating the blue area. And if the blue area is infinite, any overestimation of it must also be infinite. Okay, but what about convergence? So far, this only shows why a divergent integral leads to a divergent series. But what if the integral converges? Let's consider another series that is similar to the harmonic series. 1 plus 1 over 2 squared, plus 1 over 3 squared, and so on. If we play the same game we just did, and take left-oriented Riemann rectangles for the graph of 1 over x squared, we get, like before, that the total area of the rectangles equals the sum of the series. If you recall, the integral of 1 over x squared from 1 to infinity is finite, equal to 1 in fact, which means the blue area is now finite. But since the rectangles are overestimating the area, we don't know whether the area covered by the rectangles is finite or not. They may overestimate the blue area by a finite amount or an infinite amount. But we can change this overestimation into an underestimation with a slight change in the picture. Instead of taking left-oriented Riemann rectangles, let's make them right-oriented. The rectangles are now pretty clearly underestimating the blue area, and since we already know the blue area is finite, the total area covered by the rectangles must also be finite. You may have noticed that what we've got here is not exactly the same series we started with. In shifting the rectangles to be right-oriented, I simply deleted the first rectangle whose area was 1. But if I add 1 to a finite number, I get another finite number. So indeed, the original series has a finite sum. All right, let's try it out. So let's go and try to decide the convergence or divergence of some series using the integral test, if we can anyway. All right, so the first one that we'll look at is this one. So sigma sum of n equals 1 to infinity of n divided by n squared plus 1. All right, so according to the integral test, what we're going to do is we are going to consider instead the integral version of the series. So that would be the integral from 1 to infinity of x over x squared plus 1 dx. All right, so this is an improper integral, so what am I supposed to do with this? So I'm supposed to swap out any infinite bounds for a variable, which I will take to infinity in the limit later on. So I'm going to convert this into the integral from 1 to t of the same thing, integral x over x squared plus 1 dx. And let's see if we can handle this. So I think this one is going to be a classic u sub, right? So we have x squared plus 1. Its derivative is more or less x, and it's directly multiplying the dx, so I think that's going to work. So I'm going to pick u to be x squared plus 1, and du will therefore be 2x dx. Divide both sides by the 2, and I get a half du is equal to x dx. All right, so let's go ahead and do the substitution then. So I'm going to pull the 1/2 outside as usual. So I guess I should change the bounds as well. So bounds, just plug in each of these x bounds into the formula for u. So plug in 1, and I'm going to get a 2. Plug in t, and I'm just going to get t squared plus 1. And what happens on the interior? So x dx converts into the 1/2 du. I already got the 1/2, and du will be handled later. And x squared plus 1, that is just 1 over u. All right, so very good. I think we can integrate that without too much trouble. So I think we're going to get a 1/2 ln of u, evaluated from 2 up to t squared plus 1. And so if I evaluate that, I'm going to get a 1/2 ln of t squared plus 1 minus a half ln of 2. All right, so integration step done. Now I just take the limit as t goes to infinity, and I think we see what's going to happen. So this is a constant, nothing changes here. But if I take t to infinity here, I'm going to have ln of increasingly big things, and ln in the limit of its inputs does go to infinity. So indeed, this entire expression goes to infinity. So the improper integral diverges. And the integral test says, well, if the improper integral version of the series diverges, then so does the original series. So diverges is the answer. All right, so not bad, not bad. Let's do another one. So sigma sum from n equals 3 to infinity of 2 over n squared plus 9. All right, so in this case, our index is starting at n equals 3. So you might be concerned about that because the integral test is stated in terms of n equals 1. But it turns out, unlike geometric series and the sum formula for that, the integral test doesn't really care where you start a series. So we can just convert this one straight away into the integral from 3 to infinity of 2 divided by x squared plus 9. All right, so we know the drill. I need to convert that into a proper integral by putting a variable where the infinity is. And I think I'm going to rewrite the 9 as 3 squared in order to hopefully ring a bell for a pattern. So I think we do know how to integrate this one pretty much directly. This is a classic incidence of the arctan formula. So if you remember, the arctan integral said that if you have the integral of 1 divided by x squared plus b squared, this is going to be 1 over b times the arctangent of x divided by b. All right, so we can make use of that here. We have this factor of 2, but that's just multiplying the entire thing, so nothing really fancy happens there. It's just, the 2 is just going to carry along for the ride. So it looks like we're going to get 2 times 1 over 3 times the arctan of x over 3. The whole thing evaluated from 3 up to t. All right, so let's go ahead and plug it in. So I think the 2 times 1/3 turns into a 2/3. And if I plug in my t, I'm going to have arctan of t over 3 minus 2/3 of 2/3 times arctan of 1, it looks like. All right, so now the task is to take t to infinity. So if I do that, I have arctangent of something approaching infinity. So what does arctan approach as its input goes to infinity? So that approaches 90 degrees, or pi over 2. And at this point, I could go and simplify this down a little bit. I could go and evaluate what arctan of 1 is. It's pi over 4. But we really don't need to do that. The main point is that, well, this is a number. This is another number. The difference between two finite numbers is also finite. So we have, in this case, a convergent integral, and therefore a convergent series. All right, so far so good. All right, so let's go and do one that's a little more interesting, I think, which I know will make you all quake in your boots, but that's what math does, I guess. All right, so in this case, how about this one? So we have sigma sum n equals 1 to infinity of n squared divided by n squared plus 9. All right, well, we know what to do. We're supposed to convert this thing into an integral. So this is the integral from 1 to infinity of x squared divided by x squared plus 9. Going a little too fast. Let me not forget my dx. dx. And I'll convert the improper integral into a proper integral. All right, so now we need to go and integrate this thing. So how are we going to do this? So this is it's not going to be a u sub, I don't think, right? Because we have quadratic on bottom and quadratic on top. So what are we going to do? Well, so one thing I note is this is a rational function where both the top and the bottom have the same degree, an equi-heavy rational function, if you will. So in that case, we can approach this using polynomial long division again. I know you all missed that. I should have a little more room for that. Let me do it right over here. Here we go. Fortunately, this one is pretty short. If you're dividing two polynomials of the same degree, long division is pretty short, actually. So how many times does x squared plus 9 go into just x squared? Well, it goes into it once. Multiply it through, and we have x squared plus 9 coming out, and we need to subtract this. Subtract both terms. So again, don't forget to distribute your minus sign. The x squareds cancel, and we're left with a minus 9, which is lower degree than the divisor. So that is the remainder. All right, so the integral we wind up getting then is the integral from 1 to t of 1 minus 9 divided by x squared plus 9 dx. All right, so we'll have at it. So integrate this. Well, 1 is just going to turn into x. Nothing fancy about that. What's this guy going to do? So this is another arctangent, I think. This is x squared plus 3 squared, except we have a multiple of 9 this time. So we have 9 times, I think, a 1/3 times arctangent of x divided by 3. All right, evaluated from 1 to t. All right, so let's see what this gives us. So if I plug in t, I'm just going to have t minus 9 times a third. That's the same thing as 3. 3 times the arctan of t over 3. And plug in 1, I'm going to have a minus 1 plus 3 times the arctangent of 1/3, it looks like. All right, so now we'll take t to infinity. So if I do that, t shows up in 2 places. Over here, t is, well, it's going to go to infinity, right? So that looks bad. But let's make sure that this is really going to infinity and we're not getting an indeterminate form like infinity minus infinity. What happens to this guy as t goes to infinity? Well, arctan of something going to infinity goes to a finite number, pi over 2. So this thing, I'm not going to bother to write out what it is, but we know that it's finite. And of course, everything else over here is also finite. So infinity minus something finite is still going to be infinite. So this is a divergent integral and also series. All right, now some of you might have been slightly annoyed at this whole process because you thought of maybe a better way to do this, and you have been mashing the fast forward key either to get past this problem or see if I was going to mention it. So yes, indeed, I am aware of that. So yeah, if you're paying attention here, there's actually a bit of a shortcut you can do to avoid all of this stuff, actually. Because it turns out we can answer the question of whether this series diverges or converges without using the heavy machinery of the integral test. We can actually use the good old divergence test, right? Because if we look at the terms, just the terms were n squared over n squared plus 9. If I take the limit as n goes to infinity of this, what am I going to get? This is an equi-heavy rational function, so the limit is going to be the ratio of the leading coefficients, so that's just going to be 1 divided by 1. The limit is 1. The limit of the terms is 1, which is not 0, which implies divergence by the divergence test. Yep, so this serves as a good reminder that whenever you're given a series in the wild, as it were, a good first thing to try is just the divergence test, because it's so fast. And sometimes you get rewarded for it. A lot of the times, a series is excuse me, is complicated enough that the divergence test doesn't tell you anything. But sometimes you luck out, and you can just shortcut a problem in like 10 seconds by trying the divergence test and discovering, oh yeah, I guess it does diverge. So anyway, something to keep in mind. Okay, so I have one more for you guys, which I also think is a fun one. Let's take a look at this. So sigma sum, starting from n equals 1 to infinity, of sine squared of n pi. All right, well, if we're doing this with the integral test, what are we supposed to do? We're going to get an integral from 1 to infinity of sine squared of x times pi. All right, so this is something you can, if you go through enough trouble, actually evaluate yourself, going through all of the algebra and all of that. You can use the half-angle identity and a u substitution to get rid of the x pi. But it turns out we don't need to go through all that trouble to see what happens here. A graph is good enough for our purposes. So it turns out that the graph of sine squared of any coefficient times x looks more or less like this. So it looks something like that, repeating in a cyclic fashion. So this is x, y, and we're plotting here y is equal to sine squared of x times pi. So I'm finding the area from 1 to infinity. That will, I'm not sure where 1 is in this picture. I'm just going to say it's right here. I don't know. But it'll look something like this. So it'll be some starting point, and then we'll just shade in all of these humps. And it just keeps on doing that forever and ever and ever. And since these humps are just copy-pasted forever and ever, and each one certainly has a non-zero area, I don't know what the area is, but it ain't zero. If we go and add some constant area to itself, copy-pasted infinitely many times, it doesn't really matter what this area is. If it's not zero, and you copy-paste it infinitely many times, you're going to go to infinity. So this thing, without really doing any work, has to be infinity, which is divergent. Make sense? Well, turns out that's actually wrong. So, nope, turns out that this series does not diverge. This series actually is convergent. So the integral, I mean, this is still correct. The integral here does diverge, but it's incorrect to say that the series diverges. This series converges. And if you don't believe me, just look at the first few terms of this series. If I was to go and write them out, let's see here. So I have sine squared of, I guess the first one would be pi. So sine squared of pi is going to be, well, sine of pi squared. So sine of pi is 0. Square that, and it's still going to be 0. So I'm going to get 0. And then I'm going to have sine of 2 pi, which is also 0. And then square it, so it's still 0. So this is just me adding 0 to itself over and over and over again, which, of course, is going to equal 0, which is certainly convergent. The most boring kind of convergence you can have. So what's going on here? Did I lie to you? Is there something wrong with the integral test? Can you see any problem here? Why is the integral saying it diverges, but the series is pretty clearly convergent? So at this point, I would like, again, to ask you guys to pause the video and see if you can think it through. What's the weird thing that's happening here that's making this break? Come on, I know you can pause it. It's not that hard. It's just the two little vertical bars. You can find them. I'd encourage you to make friends with it. I'm sure you've been making very good friends with the fast forward button. It's about time you got to make friends with the pause button. All right, well, that wasn't so bad, was it? All right, so what is going on here? What is the problem? So to see what it is, it's actually a little bit subtle. Let's go and look at what the precise statement of the integral test was again. So if I go and look at it, what does it say? It says, given a series whose terms, a sub n, are determined by some function, f, which is supposed to be continuous, positive, and decreasing. And so here is where where everything is hinging in this case. So the integral test only works if the continuous function that you are converting the terms of your series into is a decreasing function. But in this case, sine squared of x pi, this is a wavy sinusoidal function. This is definitely not decreasing, which means the integral test does not apply. So you can't use it in this case. You would have to use some other kind of test. Or not any test at all, just write out the terms and you see it converges. All right, as I mentioned before, the integral test does not say that the sum of the series equals the value of the improper integral that you convert the series into. But although the improper integral itself does not equal the sum, it is related to the sum, and, in fact, gives us a way to approximate the sum of a series and, importantly, measure how good our approximation is. The idea is we approximate the sum of a series by adding up only the first n many terms of the series, like the first 10 terms, or the first 100 terms, or the first 1,000 terms. That is, we approximate the sum of the series by the nth partial sum of the series. In this case, the error of our approximation is simply the sum of all the remaining terms we did not add up as part of the partial sum, i.e. the sum of all the terms coming after the nth term. The sum of all these remaining terms is called the remainder, and the basic principle behind the integral test gives us a way to estimate this remainder. The estimation of the remainder goes as follows. Suppose the integral test indicates that a series converges. In this case, the remainder that is left over after adding up the first n terms, which we'll call r sub n, must be bounded by the following integrals. The integral of f from n plus 1 to infinity as a lower bound, and the integral from n to infinity as an upper bound. To understand why, let's take a look at the situation graphically. We want to estimate the remainder after adding n many terms, so I'm going to start labeling the x-axis here at n. Remember, the remainder is the sum of all the terms of the series that come after n, so starting from the n plus 1 term and going on to infinity. Like before, if we have a graph of the function f, we can visually represent this sum by Riemann rectangles of width 1, and for now, I'm going to make them left-oriented, so their top left corner corresponds to the height of the curve at that point. Thus, the total area of these rectangles is the same as the remainder. If I now shade in the area that corresponds to the integral from n plus 1 to infinity of the function f, you can see pretty clearly that it underestimates the area covered by the rectangles, thus giving rise to the lower bound appearing in the estimate. Okay, but what about the upper bound? According to the remainder estimate, the integral from n to infinity is supposed to overestimate the remainder. But looking at the picture, it's kind of hard to tell if it really does. That is, it's hard to say if the blue area really is larger than all the red rectangles combined. However, once again, I can play the same trick with the rectangles that I used before. If I shift all of the rectangles to the left by 1 unit, thus turning the rectangles from being left-oriented to being right-oriented, you can see that they all fit neatly inside the blue region, which means, of course, that the blue area is larger. But we're not done yet. We can actually use this remainder estimate to squeeze out one more useful result about the true sum of a series. Remember that the remainder, r sub n, is just the sum of all the terms that are not a part of the partial sum, s sub n. Thus, the sum of both has to be the true sum, s. Therefore, I can convert these bounds on the remainder into bounds for the true sum of a series by simply adding the partial sum s sub n to all sides of the inequality. All right, so let's try out this new toy on some example problems. So first one up, let's consider this series. Sigma sum, n equals 1 to infinity, of 1 over n cubed. All right, so it turns out that this series is convergent. You can verify that for yourself using the integral test if you want to. But I'm just going to take it for granted for now. And so what we wanted to start off doing is let's find what its third partial sum is, so S3. What is S3? And let's get some lower and upper bounds. On the remainder. So R3, all of the terms that we are not adding up. All right, so first things first, S3. What is that? Well, that's just the sum of the first 3 terms. So in this case, I think that would be 1 plus 1 over 2 cubed plus 1 over 3 cubed. And if you crunch that together, I think you get that this is 251 over 216, which turns out to be 1.162 and etc. So something like that. All right, so now let's see what the remainder is. Not what the remainder is, but an estimation of the remainder. So basically, we want to find the error in making this approximation for what the total sum of the series is. All right, so according to the integral test remainder estimate, the remainder, R3, is going to be bounded from below by the integral from n plus 1, which in this case would be 3 plus 1, so 4, to infinity, of the function 1 over x cubed. So that's going to be a lower bound for R3. And the upper bound, or an upper bound, comes from the integral starting from 3 to infinity of the same function. All right, so we've done a few improper integrals already, so I think I'll leave it to you to go and compute those on your own if you so desire. I'll just go ahead and skip ahead to what these turn out to be. So it turns out that this integral winds up being 1 over 32. And this one winds up being 1 over 18. All right, so we are at worst, in the worst case, off from the true sum by an amount 1 over 18. Plus or minus 1 over 18 is how, well, I guess, so yeah, so that would be the worst case error in using this 251 over 216 as an approximation to the true sum of the series. All right, so that's lower and upper bounds for the remainder. So now let's find upper and lower bounds on the actual sum. So the actual sum, which I will call S. Bounds on the total sum, capital S. All right, so the key idea that we're going to use is that S can be expressed as the partial sum S3 plus whatever its remainder is, right? I mean, that's kind of just by the definition of what remainder means. All right, so in that case, I can convert these these bounds for the remainder into bounds for the total sum if I just go and add S3 to all sides. So if I add S3 to all sides, we get the following bounds. And written out a little more explicitly, S3 we computed was 251 over 216. All right, and that turns out to be about 1.193 for the lower bound, and 1.217, and etc. for the upper. All right, so now let's turn to a slightly different question, which in some ways I might argue is more practically useful than that. So what we just did is we we decided in advance how many terms we wanted to add up, and we wanted to find out, okay, what's the error in that approximation. So now I want to turn that around, and let's say that we have a certain preordained tolerance for the error, and we want to find out how many terms do I need to add together in order to ensure that we meet that tolerance. All right, so in this case, what I'm saying is, so how many terms do we need to add to ensure we get within 0.0001 of the true sum, or in other words, we get within 10 to the minus 4 of the true sum. All right, well, remember, we already have, let me back up a moment. So this is, again, following the same flavor that I'd mentioned some weeks ago about a common sort of way to approach a problem in math and in other situations is you have something complicated, like the remainder or the error, and you want to ensure that it's sufficiently small, and so the way that we do that is we ensure that some upper bound of the complicated thing is within the tolerance. If an upper bound of the complicated thing is within tolerance, then the complicated thing itself must also be within the tolerance. And so we do have a upper bound for the error in any such approximation of the sum of a series. So the remainder, after adding up capital N many terms, whatever that is, we do know that that can be no bigger than the integral from n to infinity of the function 1 over x cubed, in this case, dx. And so our goal then is, well, so we don't know what this thing is, although we can compute this thing if we go through the trouble. And so what our goal is to find out what value of n forces this upper bound to be within, or to be less than 10 to the minus 4. So this is what we want to happen. If we force the upper bound to be within the tolerance, then the true thing has to be within the tolerance. All right, so that's the goal. So we'd better go and try to write this out in a more algebra solving friendly kind of way, right? So let's go ahead and integrate that. All right, so this is an improper integral, so let me write it out to the side. We're doing kind of a sub-problem right now. I want to write this out in a non-calculus-y kind of way. I want an algebraic expression. All right, well, I know what to do. This is an improper integral, so I need to convert it into a proper integral. All right, so I think this thing winds up being, if you integrate 1 over x cubed, I think we're going to get a negative 1 over 2 times x squared, I think, evaluated from n to t. And a usual trick, I have a negative here, so I'm just going to get rid of it by switching the order of the bounds. So I'm going to write it as a positive 1 over 2x squared, evaluated from t up to n. All right, and plugging those in, I get 1 over 2n squared minus 1 over 2t squared. And in the limit, as I take t to infinity, this term is going to vanish. And so we're just going to get 1 over 2n squared. All right, so that's the value of the improper integral that I'm interested in. So let's go and put it back into context again. So what we have is we want to find n such that 1 over 2n squared has got to be less than or equal to 10 to the minus 4. All right, well, this is just an inequality, so let's go ahead and solve it. I think we know how to do that. So I'm going to multiply both sides by 2n squared, or actually, not 2n squared. I think I'm going to just multiply both sides by just n squared. There's no reason to drag the 2 along. And I'm going to divide both sides by 10 to the 4th. So in essence, the n squared and the 10 to the minus 4 are going to swap places. So we're going to get 1 divided by 2 times 10 to the minus 4 is less than or equal to n squared. So I think I'm going to flip the inequality around. So let me write that instead as n squared is supposed to be greater than or equal to 1 over 2 times 10 to the minus 4. And with a little cleanup, I think we can get a nice round number for this. So 10 to the minus 4 in the denominator is the same as 10 to the 4 in the numerator. And 10 to the 4 is a fancy name for 10,000. So we have 10,000 divided by 2, which is 5,000. All right, so ultimately we need n squared to be greater than or equal to 5,000. But we want to know what are the conditions on n itself. How many terms do we need to add up? All right, well, I'll just take the square root of both sides. So in that case, we're going to get that n needs to be greater than or equal to the square root of 5,000, which turns out to be about 70.7. All right, so that's pretty good, although it's a little awkward to be talking about n being greater than or equal to some irrational number like that because, well, n is supposed to be an integer. But that's okay, we can fix that. So this condition is still true. We need to add up, in order to ensure that we get within the specified tolerance, we need to make sure that our integer n is greater than or equal to 70.7. So what is the smallest integer that guarantees that? Well, that has got to be the next integer up from that, so 71. So as long as we go and add up at least 71 terms, we are guaranteed to meet this criteria, or this criterion, which will force the remainder to be within the tolerance we want. All right, so I have one more example for you guys in this spirit. So example 3. So in this case, we're going to consider the series sigma sum n equals 1 to infinity of 1 divided by n times the quantity 1 plus natural log of n squared. So once again, you should be able to verify that this converges by the integral test, but I'm just going to tell you in advance that it does. Converges by integral test. All right, and so the first thing we're going to ask is, let's go and estimate the error in using the sixth partial sum as an approximation for the true sum. All right, all right, that's the same as just estimating what R6 is. R6 is the error in using S6 as an approximation for the sum. All right, so we're looking to estimate R6. All right, and we know what the bounds on this are supposed to be. First one up is going to be the integral from 7 to infinity of 1 over x times 1 plus ln of x, all squared dx. And the upper bound is given by the integral from 6 to infinity of the same thing. All right, so I'll leave it to you guys to go and actually evaluate these improper integrals yourself. Turns out what we're going to get is on the for the lower bound, we're going to have 1 over 1 plus ln of 7. And as for the upper bound, we're going to have 1 over 1 plus ln of 6. And so what that winds up being approximately is, if you use S6 as an approximation for the true sum, the error is going to be roughly between 0.339 and 0.358. All right, so you're going to be off by about 1/3. Okay, so that's that. So now for the inverted question. So let's say that we want to have an accuracy to within 0.001, let's say. So how many terms do we need to ensure accuracy to within 0.001, or in other words, 10 to the minus 3, 1/1000th? All right, so we know how to do this. So we have an upper bound for any remainder is given by the integral from n to infinity of the of 1 over x times 1 plus ln of x squared dx in this case. And so the goal is, well, we don't know how to bound this exactly, but I can certainly bound that thing, or at least that is the hope. So we want to bound the upper bound of Rn by 10 to the minus 3. All right, so again, I'll leave it to you to compute this on your own. Turns out what you get is 1 over 1 plus ln of capital N. All right, so let's solve this for n and see what we get. All right, so I think what I'm going to do again is I'm going to multiply and divide by these two things, which will cause them to switch places. So if I do that, I'm going to have 1 divided by 10 to the minus 3 is less than or equal to 1 plus ln of n. If I turn that around a little bit, oops. So I'm going to have 1 plus ln of n needs to be greater than or equal to 1 over 10 to the minus 3, which is probably better written as 10 to the 3, or in other words, 1,000. All right, so now I just need to solve this inequality. So subtract 1 from both sides, and I'm going to get ln of capital N needs to be greater than or equal to 999. And then the only thing left to do to isolate n is to go and exponentiate both sides. So in that case, take e to the power of both sides, and I get that n needs to be greater than or equal to e to the 999th power, which, if you didn't already guess, is a stupid big number. Turns out that it is approximately 7.25 times 10 to the 433rd power. So what that's saying is, you want to get if you want to get an approximation of the sum within 1/1000th, within 3 decimal digits, basically, you're going to have to add up, well, that many terms. So basically 7 followed by 433 zeros. So good luck asking Wolfram Alpha to do that. All right, but this is still actually useful information, though. So it's not quite what we wanted. We wanted to have some hope of actually being able to approximate this thing without too many terms. But it turns out that if we want to get this accuracy, we would have to add up way too many. So what that means is we're not going to be able to find the sum or approximate the sum just doing the most simple thing, which is, okay, just add up the first so many terms and then just stop. You would have to do something more clever in order to find the sum. But that's still useful information. It tells you how what is likely to be a good approach to solving the problem. If you really need the accuracy to be within this tolerance, then you know not to try adding up the terms manually.